Previously, we learned about terminology, the various words we use to describe reinforcement learning problems, which allow us to solve reinforcement learning problems. Now that you understand concepts such as agents, environments, policies, states, actions, and rewards, we can build on this. The goal is to have a framework, which we can then use to find solutions. So at this stage, we are still working to more accurately and more narrowly define a problem. Once we have an accurately defined problem, we can work within this framework and whatever assumptions it involves to derive solutions. The main assumption we make in reinforcement learning is the Markov assumption. This is something we often discuss in terms of Markov models and sequence modeling, but let's review it here anyway. The Markov assumption goes like this. Suppose we want to predict whether tomorrow will be rainy, sunny, or cloudy. Perhaps your idea may be to base this on whether it was rainy, sunny, or cloudy in the past 7 days. Well, the Markov assumption is that tomorrow's weather doesn't depend on all of the past 7 days, only the immediate previous day. Here's another example of the Markov assumption. Suppose I want to predict the next word of a sentence. I tell you that the previous word in the sentence is lazy. The Markov assumption is that the next word only depends on the previous word. Therefore, if the Markov assumption is true, then you should be able to predict the next word in my sentence. Of course, things are not so easy. You might think, because you are taking a course by the lazy programmer, that the next word in the sentence is programmer. But in fact, that's not what I had in mind. Now let's suppose I tell you the full sentence so far is, the quick brown fox jumps over the lazy. Of course, we know that, since we've seen this example many times, that the next word is dog. So you might think, this Markov assumption thing doesn't really seem to be a great idea. In fact, there has been some work in reinforcement learning where they do not make use of the Markov assumption, although that is outside the scope of this course. The Markov assumption has actually been quite successful so far. In general, the Markov assumption states that the probability of the state at time t depends only on the state at time t minus 1 and not on any state that came before that. Now, by itself, the Markov assumption is weak. But as you recall, I said earlier that we can make the state whatever we want. So if we want to make the state 3 or 4 words long, that's fine too. The words are merely observations, but the state is made up of a sequence of observations. In this way, the Markov assumption is not as bad as you might initially think. So why do we need to know about the Markov assumption? This is because reinforcement learning problems are commonly described as a Markov decision process, or MDP. Previously, we discussed the Markov assumption in terms of a state only. But as you know, reinforcement learning problems involve other objects as well, namely actions and rewards. So the way we describe an MDP is to use the state transition probability. It's the probability of arriving in the state at time t plus 1 and getting the reward at time t plus 1, given the state at time t, and taking the action at time t. Another simpler way of writing this without time indices is just to write p of s prime and r given s and a. Note that because the reward r has no prime symbol, the prime symbol does not indicate time t plus 1. You get the reward at time t plus 1 for arriving in state s prime, but we do not put a prime symbol on r. So I just showed you the most general way of writing down the state transition probability, but often we can make it less general. For example, if we are solving a maze, then most likely we are going to make the reward deterministic. In other words, there's no need to represent it as a probability distribution. In this case, we can use the notation p of s prime given s and a, and the reward can be a symbol all by itself, usually denoted as r of s prime. This encodes the idea that we were in state S, we performed action A, and we arrived in the next state S prime. We can even just say R of S or R of S prime in the case where the reward depends only on the state where you arrive at, which is actually quite common. An important point to consider is, what is the usefulness of the state transition probability? You can imagine that if we are playing some game like Breakout on Atari, it is very unlikely we will ever be able to calculate these probabilities, given that the state space would be infeasible to enumerate. And in fact, for Q-learning, the main algorithm we're going to discuss in this section, this probability is not used at all. I want you to think of the MDP and the state transition probability as stepping stones. They are simply conceptual tools, which we will use to further advance our knowledge and take us to a point where we can actually come up with a practical algorithm for reinforcement learning. In other words, while we're not going to be using state transition probabilities directly in Q-learning, they do help us build on what we've done so far so that we can actually arrive at Q-learning in a logical manner. Why else is the state transition probability useful? Imagine a game like tic-tac-toe. You might think there is nothing probabilistic about this game. When I write down an X or an O, that's where the X or the O goes. Why is there a probability associated with that? Why is my action not deterministic? And in fact, it is entirely possible for your action to deterministically bring you to the next state. Imagine, for example, a classic task known as the inverted pendulum. In this reinforcement learning task, your job is to control an upside-down pendulum so that it does not fall down by moving the cart left or right as necessary. Now, you might think to yourself, how do we describe such a system? Well, we use the laws of physics. And now think to yourself, are the laws of physics not deterministic? For example, when we learn Newton's 3 laws of motion, do those laws of motion involve probability? The answer is no. So then, what in the world do we need probability for? The answer is that your state may not completely capture all the possible information about the environment. Consider tic-tac-toe again. In tic-tac-toe, there is another player. That player's moves cannot be predicted by a tic-tac-toe agent. Therefore, there are multiple possible moves that could occur between the agent's previous move and the agent's next move. If we're talking about physical systems, we also have to take into account chaos theory. That is, even if you know the exact laws of motion, this does not mean you can accurately predict the future. In fact, the further into the future you try to predict, the more unreliable your predictions become. Sometimes we refer to the transition probability as the environment dynamics, which makes sense when you think about it in the context of physical systems. A system like an inverted pendulum is in fact a dynamical system. The last thing I want to mention in this lecture is to bring us back to this picture, which you've probably seen several times at this point. An MDP, or a reinforcement learning problem, consists of these two objects, the agent and the environment, going back and forth. The agent reads the state from the environment and decides what action to take. It takes that action in the environment. The environment is updated based on that action and brings the agent to the next state, while also returning an associated reward. The agent can then read this next state, take the next action, and so forth. So they just go back and forth in this circular pattern. What we've done so far is to represent both of these objects with probabilities. The environment is represented by the state transition probability P of S prime and R given S and A. The agent is represented by the probability pi of A given S. This is more helpful than you probably realized at this point. By representing both the agent and the environment as probabilities, it allows us to describe reinforcement learning problems mathematically. In particular, once we have an equation, we can solve that equation. Without an equation, there isn't really anything to solve. That's a pretty deep insight. In order to come up with a solution, we have to have a well-defined problem. Using mathematics, specifically probability, allows us to create this well-defined problem, and that's the first step towards finding a solution.